Hello everybody, and thank you for joining our webinar today on Sustainable Advanced Materials for a Low Carbon Future. My name is Professor Paul Meredith and I'm a Professor of Physics at Swansea University. I'm also a Say Cymru National Research Chair and our research is funded by the Welsh Government's Say Cymru True Programme. So the theme of today's webinar is really semiconductors and how since about 1950 they have fueled our high-tech lifestyle and particularly given us the vast array of electronics that we have in our modern life, such as our smartphone and our computers. And really we're going to look at the question of whether we can expend the available carbon budget that we have in this climate crisis that we face to sort of fuel this continual expansion of our electronic high-tech future. And I want to introduce the concept of embodied energy. That is the amount of energy that goes into making something and how we can minimize it in order to reduce the carbon budget load. I'll tell you about some of the work that we're doing here at Swansea University Physics Department on the development and understanding of what we call sustainable advanced materials. That is looking at ways of taking our existing semiconductors and new semiconductor materials in particular and making them more sustainable. And at the end, I'll discuss a vision of the future that we have here, the idea of bringing together different semiconductor platforms to create new technologies. If you're interested in anything I've said, you can find it all on our website, on our knowledge sharing portal, advancedmaterialsswansea.co.uk, and the address is there for you. So let's start off with a brief history of how we came to where we are with the use of electronics and semiconductors. This photograph that I'm showing here is of three very famous physicists, William Shockley, John Bardeen and Walter Brittain. And these guys in the United States in the 1940s developed the first semiconductor-based electronic devices. And this little device I'm showing you here was reported in 1950. And this is the very first semiconductor solid-state transistor. It doesn't look very much, but it's a blob of germanium sitting on a contact pad acting as a transistor. And within a very short amount of time, maybe as little as 4 years, these types of prototype transistors were being made into fully packaged devices. Here's a Texas Instrument transistor from 1954, which you can see is smaller than the size of a stamp. And very rapidly, these types of devices became integrated into small circuits. Here's a prototype integrated circuit that was actually used in the Apollo space program to send man to the moon in the 1960s. And within a very short amount of time, indeed, fully integrated high-density transistor circuits, the so-called silicon chip, was developed and that enabled things like personal computers, where you could pack a lot of computing power into a very small space. And was the start really of the big revolution in computing in the 1970s and 1980s. Fast forward to 2020, and I'm speaking to you from my laptop in my office, which is a very powerful computer, vastly more powerful than the computers that we use to send man to the moon. And of course we have our smartphones. Smartphones contain an array of semiconductor-based devices, silicon-based devices, and also very, very high performance compound semiconductor-based devices, which we'll talk about in a second. But the smartphone is absolutely packed with electronic and semiconductor technology. Of course, we use semiconductors for other things as well now, and I'm showing you here as well a large silicon semiconductor-based solar panel, which has got silicon-based photovoltaic cells to convert sunlight into electricity. Going forward, what the future looks like, of course, is anyone's guess, but we do know that we're going to need advanced semiconductor power electronics to drive our transition to electrification from fossil fuel transport. The Internet of Things is already with us. The connections of multiple semiconductor-based devices which are doing sensing and control. And ultimately, the end point of the journey, many people think, is a full integration of electronic systems into biology, with maybe the ultimate concept of a fully electronic brain, where us as humans are interfaced seamlessly with electronic technology. That field is called bioelectronics, by the way. So what I'm showing you here really is nearly 100 years of human evolution enabled by semiconductors, and particularly enabled by semiconductor physicists and engineers and material scientists who develop these things. So what's the problem with this vision? Well, the problem with this vision really can be encapsulated by this simple image. We all know that we're living in a warming world. That climate change is driven by man-made emissions from the burning of fossil fuels largely, and through things like agriculture. We're releasing carbon dioxide, nitrous oxide, methane into the atmosphere at a rate which is causing the planet to warm. And a considerable portion of the world's electrical power is still generated by the burning of fossil fuels. And this has implications for this high-tech agenda. And we can in fact start defining and start understanding how much energy it takes to make a high-tech gadget like our smartphone. And this concept is called embodied energy. How much energy do we have to put in to make the thing that we use every day as a phone, as a smartphone, as a computer? And it turns out that to make a smartphone takes about 0.25 gigajoules per phone. So that's 0.25 times 10 to the 9 joules of energy. A laptop, 4.5 gigajoules. And you have to ask yourself the question, what happens to that energy after the smartphone is thrown away or not recycled? And similarly, the laptop, we typically use the laptop for 3 to 5 years, smartphone probably about the same. So that's a question of what we do with this embodied energy. And there's another problem as well. This is a graph I'm showing you here, which shows how much energy we use, how much power and energy we use in the big data centers. Obviously, the cloud requires energy to drive it. And when you take a photograph on your smartphone and you decide to store it on some form of cloud, that requires energy. And we can see on the right-hand side of the graph that 10% of the world's power generation was used to power data centers in 2020, and it's predicted that will be 40% by 2030, which is completely unsustainable. So every time you take a picture and you upload it to the cloud, just think about the energy that you're using to both upload it, to store it, and to keep the data centers efficient. A lot of that goes into cooling because the storage devices generate a lot of heat. There's another problem as well, particularly for some of the really high performance semiconductors that are in your smartphone. This is a periodic table of elements that was produced by the American Chemical Society recently, and the elements in red are ones that we would say are endangered. In other words, are in danger of being depleted within the next century on the Earth. An important one is actually gallium, which in combination with arsenic makes gallium arsenide, which is a very, very important compound semiconductor, which is the basis for a lot of the componentry in high-speed electronics, RF electronics, and on our smartphone as well. So we have this concept of not only having a carbon budget, we have the concept as well of having a kind of elemental budget to play with, which is going to have to make us think about, number one, how we recycle these elements, number two, how we make the manufacturing of the compound semiconductors particularly very, very efficient, because they are the highest performing materials on the planet, and at the moment we can't do without them. So we've got to think about these two things. What we also have to think about is potentially developing new types of semiconductors, which maybe don't have such a high performance and can't make such fast switches, but can do other things that can relieve the pressure, if you like, on the traditional semiconductors. And if we look particularly, for example, at the silicon cycle, silicon is the most ubiquitous semiconductor, as we've said, was very much the first one to be integrated into electronics. We make silicon from sand. And sand is silicon dioxide amongst other oxides, and fine processing of sand to create highly crystalline, very, very pure silicon takes a lot of energy, high temperatures, for example. And the question of whether we can develop new semiconductors which don't require as much energy to process and to make and to turn into devices is a very, very interesting question, and one that we think about a lot here in our group at Swansea. I'm showing you two semiconductors here that fall into that kind of category. This semiconductor here is an organic semiconductor made of hydrocarbons, and this semiconductor here is a so-called perovskite semiconductor, and it's a hybrid organic-inorganic material. Both of these semiconductors can be dissolved in an appropriate solvent and can be made into devices by casting the solution of them onto an appropriate substrate and built up into layers. And that is a very low embodied energy process, doesn't require a lot of heat, can be done at or around room temperature. And so we see these particular materials as having some utility in expanding the palette of semiconductors that we have available to us and not adding more to the carbon budget. They also have very different physics. The physics of silicon and other highly crystalline semiconductors was kind of worked out in the 50s, 60s, 70s and 80s. The physics of these new type of low embodied energy semiconductors, which is solution processor, appears to be quite different. They are so-called molecular semiconductors rather than banded semiconductors. And so we do a lot of thinking around the new physics that we need to understand in order to make these things useful. The other thing to note is that this type of semiconductor comes from earth abundant materials, and so that really helps us with the endangered elements story. So at Swansea Physics, we study these semiconductors and we try and make things from them. We make devices from them. I'm showing you here one of our glove boxes. Organic semiconductors in particular are quite sensitive to moisture and oxygen, and so we have to do all the processing in a nitrogen-filled glove box, and this is one of our researchers doing that at the moment. Once we've fabricated devices and made the materials, we also try and understand how they work, and we use some quite advanced simulation and theories to do this. I'm showing you two examples. The left-hand example is a simulation using finite element techniques of a grid structure for an electrode that we build these devices on top of. And this simulation here is an optical simulation. It shows you the optical field distribution in a semiconductor device stack, and for 3 different wavelengths, an ultraviolet, a red, and a near-infrared wavelength. And the semiconductor in question here is this thing here. It's called PM6Y6. It's a combination of an N-type and a P-type organic semiconductor, and this is a material that we use to make solar cells. Once we've made the devices, processed the material, maybe done some simulations to understand how they work, we do some advanced characterization and measurements in our laboratory. This is actually me last year making some measurements before lockdown using lasers. So I'm firing a blue laser and a red laser at a little photodiode, and we're measuring the photocurrent that's generated by shining that light onto the photodetector. And this is actually the result of that. This shows the efficiency with which we generate that current as a function of the color of the light that we're shining on it, all the way from the ultraviolet down here, blue ultraviolet, to the near infrared, which is 2000 nanometers or 2 microns. So that's the sort of thing we do. And the applications that we're interested in are numerous, but a couple of the main ones associated with either putting light in and getting electricity out, or putting electricity in and getting light out. These are so-called electro-optical or optoelectronic devices. And one such example is light-emitting diode technology. We make light-emitting diodes out of organic semiconductors, and we're particularly interested in making quite large area emitting devices that we can use for strip lighting and things like that. So we do a lot of work and a lot of thinking around that. I'm going to talk about solar cells in the next slide, but photovoltaics using perovskites and organics is a big part of what we do, a very important part of what we do. I'll say a bit more about that in a second, but suffice to say this is a 5 centimeter square plastic solar cell made from organic semiconductors. And we're also interested in making photodetectors and imaging systems. And here's an example that we came up with a couple of years ago. This shows you 3 types of photodetectors: a blue sensitive photodetector, a green sensitive photodetector, and a red sensitive photodetector. And this it mimics the light response in the human eye. And we're particularly interested in these systems for making things like artificial vision, machine vision, and ultimately maybe even artificial retinas for people who have retinal damage. So that's something we're very interested in. Another quite different application of interest to us is so-called bioelectronics. That is taking semiconductors and interfacing those semiconductors with biological systems. The current carrying entities, signal carrying entities in biology, are associated with the movement of protons and ions. And of course in semiconductors it's electrons and holes. And so we ask ourselves the question, how do we kind of glue together the signals that are carried by protons and ions with electrons and holes? So that's the field of bioelectronics, and new semiconductors are essential for that. Here's a particular example of a solar cell. And this is a solar panel, standard solar panel I'm showing you here. And many of you will have these on your roofs. They're made from silicon solar cells, individual silicon solar cells, which are these squares here. They're about 6 inch by 6 inch. And they're all connected together, and we glue them between a glass plate and a back plate to protect it all, and these things go on our roof and generate electricity for 20-25 years. The important thing to note is that the thickness of the solar cells, silicon solar cells, is about 500 microns, or half a millimeter or so. The equivalent using these new solution processed semiconductors, the organics and the perovskites, is here. Very similar concept. For example, we still take a P-type material and an N-type material, as in a silicon solar cell where we have P and N-type silicon, and we glue them between the electrodes in a very similar way that we glue the silicon between the glass plates. But the big difference is that these things are about 1,000 times thinner. So the active layer is about 1,000 times thinner than in a silicon case, and that means we don't use very much material. Okay, so that's important. It also means it's so thin it can actually go onto something which is flexible, and we can put it on a flexible substrate, as I showed you in the last slide. And some really interesting stuff coming through now in the future is combining this type of technology together. So this is an electron micrograph of a silicon bottom solar cell, and then a very thin perovskite solar cell on top of it. This is called a tandem, and this allows us to harvest more of the solar spectral region and create more electricity from the sun's energy. And so this is a so-called tandem hybrid solar cell, combining different types of semiconductors. So a few take-home messages coming towards the end of our webinar now. Hope you enjoyed it. Number one, we have all been living in what has been called the silicon age, that is the silicon electronics age. Silicon and other semiconductors has given us, since the 1950s, computers, smartphones, a man in space and on the moon, advanced healthcare, transport, the media, data communications. Semiconductors and electronics are at the heart of all of those things. But semiconductors and the other materials that go into things like our smartphone require a lot of energy to process, and so we have to ask ourselves the question how we minimize that embodied energy, and we also have to ask ourselves the question of how we maximize the use of really important semiconductors like gallium arsenide in terms of the availability of those elements on the earth, and how we recycle them, how we make our manufacturing processes more efficient as well. And our program at Swansea, we look at all of these things, but we also look at trying to understand how we can make new semiconductors to add to this big palette of materials that we have available to us, and particularly ones that have got low embodied energy, like the organic semiconductors and the perovskites that I showed you. And we're interested in applications like large area lighting, LEDs, solar cells, photodetectors, and even this concept of making semiconductors and biological systems integratable and pulling them together. Finally, before I finish, I just want to thank a few people, but say a few words on what our plans for the future are. We expect in 2022 to open a brand new state-of-the-art research facility to look at how we address some of these problems and how we actually start to combine different semiconductor systems in order to create new technologies. And it's going to be called the Center for Integrative Semiconductor Materials. It's going to be capable of doing research on silicon and advanced compound semiconductors, as well as doing research on these new types of semiconductors. So once again, keep an eye on that, and if you're interested, you can go to our web portals and see what our progress is like. I just want to finally thank all our collaborators and the people that fund our research. Particularly want to thank the Welsh Government and the European Regional Development Fund through the SIC Cymru programme for funding our research. And I thank you for joining us today. I hope you enjoyed it. Hope you've learned something. And if you've got any questions, get on our website or drop us a line.